right?
Mm-hmm.
And when I need to do function composed of R of t times the magnitude of R prime of t dt, where that's R, right? See how it's written like this? I'm saying this is R of t. It's what? T squared and dt. So can we start here? What does this mean? What does this mean? They wrote a y here. So I'm not going to leave it y. We're going to get everything in terms of t. What do I substitute there? You got it. Someone he says, this is just 8t. No, that's 8t. Why did it? It had a y. So what if this had an x? I would have put the what? T squared. What if this had xy? I would have multiplied. Did you follow me?
Mm-hmm.
Oh, we're just looking, whatever they have here, and we're substituting. Very good. Well, what goes next for this line? I have to multiply the, all right, the magnitude, which is the square root of r prime of t, which is, well, what is r prime of t?
2t and 8.
2t, is that derivative? And this derivative is 8, and I got to take the square root of
2t squared
2t squared plus
64.
64. And this is what we're doing. This is the line integral of a scalar field. Now we got to figure out how the heck we're going to evaluate this. Let me do it again. 0 to 3. Do you want to put the 8 out? I'll do it. See? What's this? Now, if you want, you might pull a 4 out of that, but I'm not going to do that. You will notice it's a u sub.
Mm-hmm.
Grid eye, look, this had a t squared, this had a t to first, so. We did 4t plus 64, what's the derivative? 8t dt, 1/8 du equals a t dt. Bye bye t dt, see you later. And I can put the 1/8 with the 8, and what do you get? We've got the line integral of the square root of u. This would be, we go, what is this again? Well, there's the scalar field, z equals y. We're finding basically the area, right, under that curve along that field there. That's scalar function. What's the square root of u? 2/3 u to the 3/2. I'm going to resubstitute. What would that be? 2/3, because only 8 times a 1/8 became a 1. 2/3 of 4t squared plus 64. And where am I going from?
0 to 3.
0 to 3. Although some of you might change the limits. That's okay too. So what's the answer? 2/3 of? What's 3 squared times 4? What's 36 plus 64?
100.
100. Minus, put a 0 in there, what do you get?
64 times 2 over 3.
Yeah. What's 2/3 times 32? 64 over 30? There's your line integral.
Didn't you forget the exponent of 3/2?
Oh, you're the best. Let me do that. Thanks, Brad. He goes, don't forget raised to the 3/2 right there. So I'll put that to the 3/2. So I'm going to do 100 to the what? 100 to the 3/2 minus the 64 to the 3/2. Brad, thanks again. What's the square root of 100 cubed?
10, 10, 10.
10
1000.
times 10 times 10, 1,000. Brad, thanks again. What's the square root of 64? Then you got to cube it. So what's 8 times 8 times 8?
256.
8 times 8 is 64, and then you multiply another 8.
512.
512. So what is 2/3 of
488.
488?
Can it calculate?
What's twice 488? I'll put a 3 underneath it. 976?
Yeah.
There you go. I'll put it 976 over 3. And Brad, thanks again, because that 3/2, you remove off it. It's like, whoa! I'm going to wrong answer. I appreciate that. Everyone okay with that? Line integral with scalar field? Hey, the next problem we're gonna do, you're gonna notice it doesn't have a ds. So you're not gonna have to figure out what the heck we're gonna do with this. Just had the ds, that's ds. So remember that, even though we for an angle, what's the ds again? Right there. You saw us derive the square root of dx over dt. It can, oh, by the way, it can have it can be three-dimensional. So what else, if this was three-dimensional, this would be the square root of dx dt squared plus dy dt squared plus dc dt squared. Cool. Well, let's look at this problem. That was number 5. Let's look at the one, look at number 7. We'll put that in the board. It doesn't have a ds. It says evaluate. There's that c for line integral, aka curve integral. We got y squared dx plus x plus y dy. Does everyone see the problem I'm referring to? This is number 7, just from the practice problem. And here's curve C. Your curve is given by x equals 2t plus 2. And y equals 3t plus 1. And it wants you to go from 0 to 1. Okay. So I'll erase all this. I'll get this out of the way. I'll leave this up here. But our first observation, I want, this isn't going to work, is it? That's a what? ds. What is ds? That's ds. This is with respect to what letter? What letter?
ds.
That's with respect to x. And you notice with the, I put this even on a notes. This line integral here is with respect to arc length. This line integral right here is with respect to arc length. This would be with respect to x. This would be with respect to y. So what are we going to do with this? You might find this easier. The first thing, most important, we're not going to ignore these. You know what I mean? We're not just going to go, put y squared, put x plus y, and do the integral. And put t's. These are important. Something has to get substituted for it. So here's the secret. Can I think of that as x prime of t? So what is dx equal to? See, we're trying to figure out what can I substitute for that dx.
X prime of t multiplied by dt.
There you go. That's what you and I are going to put in place of that dx. Everyone got that? Look, we're going to be like, you go here. Got it? Okay, what's going to go there? Let's put that. What's dy dt?
So y.
Well, that's just the derivative of the y with respect to t, y prime of t. So what is dy equal to? Y prime of t dt. Has everyone got that? That's going there. That's what they mean. Now, if you want to write, I passed out a document with those formulas, but we can put it right here. You know, what does this mean? I'll put another section. And what's the integral of some function of x and y dx? You know what that would be equal to with the line curves? I would say this is equal to, ready? Function of r of t multiplied to, what did I call dx? X prime of t times a dt. You'll see that formula right in your book. And I can now go from an a to a b. Everything is in terms of t's. See, the minute I get everything in terms of t's, you'll notice I wouldn't write a to b. Like some one t value to another t value. So hey, just remember that on a test, that we just don't do what with these. You can tell by my laughter, it happens all the time. So you just go, oh, line integral, I'll just put y squared, I'll just put x plus y, and work the problem, I'll go from 0 to 1. It's like there'll be a little bit off, because this will take on at least a number. Unless you're lucky and they're ones. Sometimes they are ones. You ready to do it? Hey, in a similar manner, what would this be? So imagine, what would this line integral of a function of x and y with respect to y?
So
a line in respect to y, what would be
say
the math formula?
y prime t.
You nailed it. I'll put a to b. Alright, thank you very much. Function of r and t. Function of r and t multiply just y prime of t dt. I'm not gonna write it, but what if it was a DZ? Same thing. Z prime of T dt, same thing. Okay, so, are you all ready to work this problem? Let's do it. One step at a time. What goes there?
3t plus 1 square.
3t plus 1, parentheses squared. Oh, what's the limits?
0,
0
1.
to 1. What goes here? What goes right next to it?
D,
What is dx? I'm going to write it. It's the derivative of x with respect to t.
dt.
Right. And what is derivative of x with respect to t? You go, what about the
2.
dt? I'll put the dt way at the end.
So that's 2, right?
What's the derivative with respect to x? Just a 2?
2
So I'll put
dt.
a 2 right there. I'll write it right below it just so you look back and go, where did that 2 come from? You can see, this is the 2. And I'm putting the dt way down here at the end. So that we can do everything in one line. Now, what's here? What's x plus y? Everyone, can you just do the math in your head? What's these combined like terms? 2t plus 2 plus 3t plus 1. That becomes 5t plus 3? Alright. Is that okay with that? So I just combine these, x plus y. Now, dy, do I ignore it? No. What does dy mean? Y prime of t. dt. Okay. But let's do it right here. 5t plus 3. And what goes here?
y prime. So
What's
that's
there
3.
y? 3. And you got it. And you just finish off the integral, right? Now you know what to do from here, right? Well, hey, can we just do one more step? We don't have to evaluate the whole thing. How would you get out of that mess? You don't need to use stuff. What would you do? I would FOIL it, right? I'd FOIL that out, expand it. What is that? 9t squared plus 6t plus a 1, and I'd multiply the what? The 2. But from here on out, it's just, what's that? 15t plus 9. Again, you don't have to evaluate the whole integral. I know you wouldn't. You know what to do now. Multiply the 2 everywhere, combine like terms, get no use sub needed. Most important to me was, you know how to evaluate this, if it's with respect to an x or y. Cool. So this leads us to the last form of what we're doing. This is fun. How about a line integral of a vector field? So this leads to that. Line integral of a vector field. You can see the formula here, everyone. It's f composed of r of t. Well, this is the vector field. Vector field, right? Function composed of that. You'll see this on when I wrote f dot dr. So this is just, let me take this. This is f for vector field f composed of r of t, dart r prime of t. But they just write f dot dr for this. But you'll notice it's going to be a dot product. Because similar to this, I don't know if you can tell. That's why I want to leave this up here for a second. Doesn't this look like the dot product was carried out?
Mm-hmm.
This times the x prime plus this times the y prime. And you bet, that's like a dot product being carried out, which leads us to now what we talked about, a line integral of a vector field. The first thing is I want you to see what it is. So I'll hit this. Power it up. This is pretty cool. What's a line integral of a vector field look like? The last one was a scalar field. What's a line integral of a vector field? So I like this applet. This is pretty cool. Fire that up. Make sure this is the source is names. Then we'll do a couple of these. Last stuff we'll be doing today, but I want to make sure we do at least a few of these. They go fast though. No worries, they go fast. And it's fading in. You're going to see a vector field. The vectors are blue. And they write the formula at the bottom. If you want to read this, the trajectory of a particle in red along a curve inside a vector field. Starting from point A, the particle traces the path C along the vector field. The dot product along that green line of its tangent vector, which is going to be the red arrow, and the field vector, which is the blue vector, all right, is what we're getting out of this. And we're just going to do an infinite sum of that. It's going to be the summation, this infinite sum limit the limit is you sum these towards infinity of all those dot products. So we'll see this again. Okay, here we go. There's the vector field. Curve C starts at A, goes to B. Now, look at the red vector and the blue vectors. Aren't they going in the same direction at the beginning? So dot product, wouldn't they be positive? Somewhere around here, you'll notice the blue vectors go against the red vectors. Watch what happens to the integral. So it's going to start right about here. Do you see what happened? Because those vectors were what? Going against, the blue vectors were going against the tangent vector, which was red. And when you do that dot product, that's actually a negative value. And so you're summing, you know, those negative values there. Did everyone see that? I want to see it one more time. Well, this was written out. At the beginning, the blue vectors are going in the same direction as that red vector. You'll notice that's given a positive area when we're going to do the integral. Right at the beginning, think of red vector as the tangent to that green path. Red's going in the same direction as blue. And then when does it go against? When does blue start going against it? Right about there. And all these were going against it. Does that make sense? So when think about it, what would be the answer to your line integral of a vector field if half the time the blue vectors went with it and half the time the blue vectors went against it? What would you probably get for your answer?
Zero.
Something like what?
Zero.
What if all the vectors go in the same direction?
It's positive.
All the vectors go in the same direction as your red tangent vector.
Positive.
Then you're going to get a positive line integral, right? And what if they all go against it? It's
Negative.
going to be negative. Does that make sense? Because sometimes that'll be asked. I'm not going to do that right now. We'll work some problems, but can we play around with that first? Because it's fast. So I'll minimize this. How about, let's see. I'm going to go to 16.1.16.2 problems, which you have a copy of. Let's go down to number